takes and has input some data, which means essentially it takes the sample, the bandwidth h, and then we are good to go, right? And then we do the estimation in some value, x value. For every, well, x are the data, and then x value is the point at which we do the estimation. So that's sort of one point. Or it could be a vector, essentially. So we need the sample size, which is the length of the x. That is the n. Because we need it for our calculation, because we need the weights. Right? So the weight is. So let's calculate the weights. Well, I mean, the weights we could indeed do, because that's, well, that's from SciPy, we can import norm. Right? So norm is the norm from the statistical part of the SciPy, stat. SciPy stats and we import norm. Right? So then we have the PDF. Right? So that we can easily calculate the weights. So, well, we can do it actually all together. You have to leave it there. This one. All right. That's exactly the same as we did with the Nadaraya Watson. So we have the weights one by one for every value. So you can do this enumeration, of course, to get the weights and calculate the averages for each case of the component. All right. So let's go back. So here then I have 4i and both of them together. Let's put this data so that I can use the x here inside my 4i and x in enumeration of x bar. Let me do the following. So then we need the weights. And what are the weights? These are the this is the norm, from the norm. Then I need the PDF. And now I have to calculate, say, the distances divided by h, and then I will do it. Right? So here then we have essentially the data minus x. So that's the value that we are indeed having inside our formula. Divided by h is closed, so that's the weights. Now we can, afterwards, so now I have the weights, all right, for a specific value in the x. And the estimate that we have for every x that we see right here, here, is the mean of the weights. For all of the weights that I have. Now I sum them, divided by the sample size, which is a mean. So here then I have f at let's put f bar, so that's the value of f at a certain point. Then it will be np.mean of weights. So we can. So here I have all of the f values, everything. is my logic okay? It's okay, I don't have any problem, right? Actually, I do need an enumeration. I don't need the height.
F value should have an underscore before the value for the return, and F underscore value.
Yes, thank you. So I don't need the enumeration because I'm not actually taking care of what it should be. And then this I also don't need because I'm using it.
Data frame.
Alright. So, I can continue. So then, well, let's generate some x values. And that will be, well, let's have a line space. Starting from x dot mean, going to x dot max, with whatever, 200 steps. Alright. Now fs becomes kb of x and h of silver now, and the x values. Now it's just plotting business. TLT dot log of we plot essentially the true values. True values that we need. We just need the x values and the f test. Hold on. And then so now let's maybe do the following. Let's do this one and let's call it as 2. Alright. So that will be the KBE. And let's say we use half of it. And then multiplied by 1.5. So a larger one and a smaller. So that we can 2 and 3. Let's have a label. And the label is h divided by half. Here we have another label, h, and then here 1.5 h. And the label here is simply h. Now we need PhD close the legend label. Now we have these. it will vary essentially the bandwidth, then things will go up and down essentially. Okay. No, it's actually very simple. It's an average. It's average of all those bits. Do you have questions? Maybe.
Professor, I'm lost on like, so what is F here? We've been trying to show the meaning of the word.
Right. So let's see. Let's actually motivate this. So the last term, or sort of the optimal bandwidth, is essentially this one. So let's maybe stay with that. And that looks like actually a very nice density. Look, I give you some data. So data points in the Excel sheet. And I'm telling you, what is the PDF for this? Estimate the PDF. You could actually say, well, okay, so if I want to understand the distribution of the data, then I can use a histogram. Oh, go use that, don't say it, just use it, as everybody does. But also one can do a little better and estimate the underlying PDF. So here there was some PDF that was used to generate those basically data points. Right? What we do here is that we estimate that PDF. I don't know the true PDF, but actually I know. And that looks like, so the estimate thereof looks like this. Okay? So that was a simple task which I sort of gave you to do. Is it now fine? You understand what we are doing?
Yeah.
We have some data, and then from those data, then we estimate the PDF. Maybe just to make it a little bit more fun. What do you see here?
Is it one of the X or from the Excel file?
Well, the data in the Excel file, yeah, based on the Excel data file, because I read them. So,
And also echoes X into it.
so your question is about these lines? Now I'm a bit lost. Maybe you should explain to me a little further. So the data, so the question is, your question is about what are these data, what are these lines? Or
I think like this line is like the predictive of the X that we have here.
that's right. So that is the estimated PDF of the data that we have in the Excel file. And that looks like this. Basically, that's the curve that we have. Yeah? And so if I give you this PDF, okay, and let's say I tell you that these are the scores of some students, they are real data, correct? That I have normalized them. They have normalized the scores of bachelor students that I had on my statistics class over many years. There were almost 1,000, there were more. So there are of many cohorts that I've had, I collected them, and then I basically added the scores as you see them as a PDF, as some data points which are normalized. So sort of are normalized. So what do you see? What does this graph tell you about my students? Can you make up some story?
So what is it? How can we have the scores of my negative?
I normalize them.
Unnormalized.
This is normalized. So transform them somehow.
So more students that is a bit like close to -1.
Yes, that's true. So you're probably the average students. Yeah. There are many average students. So that's the first big peak that you see. Right? So that's the moment that you
you have there.
So, well, that's a,
Yeah.
so many students actually, I mean, that's roughly the average, looks like. An average student was scoring here. There was some group that they were good, but there were very few. But then there's another cluster of the students which are, well, sort of well above the average. So they are above the average. Not the top ones, but they are good ones. So there were many that they were average, so they just passed. But then there were also many more. So many of them are also, well, another cluster that we have here. This, well, this second basic repeat is a very interesting one. It is a mode. By modern PDFs, always should indicate from the lamps or G. There are clusters. This is very important to keep in mind. So it means there is heteroscedasticity, average and above average. That's very important to keep in mind once you see the PDFs. If there are multimodals, modes means that you have essentially, so indicate that you potentially have some cluster in your data. That is what I have. But it would have been interesting so that I see you, show you the PDF. I don't have them beside me. But over time, how does the PDF actually do stuff? Which oftentimes one does, all right? So, for example, let's say, but oftentimes one is interested in details, also the modes, right? For example, let's say, what is the wealth distribution of people in Vietnam? All right? So then you need to basically estimate the PDF of this year, and estimate the PDF the other year, and so on and so forth. And maybe there is some shift. Maybe it sort of moves to the right. Maybe it's more or less stays the same. Maybe that there is somehow little by little the cluster is forming on the upper side. Right? So it means that sort of more and more people are getting richer and richer. I don't know. Is it like that? Do we have the data? Can we do that? Do we have somewhere data on wealth? Or somehow some wealth data in Vietnam? Or income? Income maybe, not wealth. Wealth is hard. But income potential. So one can actually maybe look at the income distribution across different years. Right? So from 70s till now, what happened? Right? So with the income distribution. That is a distribution. Right? That's the distribution of the grades. But one can do further. Right? But I mean, that's univariate. Right? Univariate is not, well, it's interesting, okay, you get some information out of that. Oftentimes we are interested in multivariate distributions. So not only the income, but also maybe, well, there may be political cycles. Right? So, well, I don't know, the Communist Party has been very stable for many years, right? But they have done a lot of stuff. Right? So strong economic growth and so on and so forth, they have done something. Right? So it means that maybe that there was some policy that was implemented, all right? So here, well, let's say we have time, so before the policy implementation and after. And then everyone can basically estimate the distribution of the wealth before and after, all right? But if it is shifted to the right, maybe the form, the taste, and so on and so forth, everyone can make up some stories out of that. Right? But then we be more descriptive. All right, so this is not somehow, as I said, so multivariation, multivariate indeed distributions are more interesting than univariate. All right? But the starting point is this. Right? And now we know that, we can now run and do more. So more indeed, what estimations. So that's not actually very fun. But going to higher dimensions comes with challenges. All right? Now let me tell you, I want to take you to multivariate. I'm going to start discussing it a little bit further. Do you have questions?
Okay, I just, can you also show, like, grab the histogram of the X so that we can see that, like, of course, I do that, but like, I cannot do it at the
So
same
very
time.
nice. That's
Yeah,
very
yeah.
good.
Yeah.
Right? So that's an excellent.
Yeah, so that's the reason why I think like, so that is why the edge of the Superman is like,
Yeah, it's true. It makes actually a lot of sense.
okay.
So look, the histogram is pretty much the same.
Yeah, yeah.
And you do it with what? With SNS or with the map program?
relevant kids, yeah, just write it, but I don't know how to like, yeah, to integrate it into one so that I can see that.
Tỷ rưỡi chắc.
I feel like the scale is different. I don't know how to divide it into 1,000.
So what you can do is doing the following. And then let's go for G, and then here there should be some option. And we do what can we do? I don't know the answer. That is how I take care of stuff.
That's such an easy show it.
Well, you can also do that. And maybe you should use SNS, Seaboard.
Okay.
Seaboard is a strong one. And so his question was that let's do a histogram and then see how good we do. Alright, so we'll work. We can do that. Let's import Seaboard as SNS. And SNS or Seaboard histogram. I don't know on top of my mind, but that is the histogram. Okay, so look over here, Seaboard has a KDE embedded. Everything we programmed is in here. Alright, so we can do the following. We can say SNS dot hist log. Let's import it first. SNS dot hist
Ủa mà nãy giờ chị Ly cứ thay đi hả?
log.
Mở có mà đúng không?
When the data here, then we have X and KDE is true. Yeah, you see? Sort of that is our curve, ours. It's not this from generated by ourselves. And this is actually the bandwidth, and this chooses the silver. And then that looks like so, and that is the PDF. So I mean, that's sort of already got it. Got it right. Alright. Well, ChatGPT is better, but it has become better, but it is still not, I don't still rely on it, because it's somehow oftentimes, I check it very often, and it has become better, but it is not clever still for my taste. With probability questions, it's oftentimes goes wrong, just gives you wrong stuff. With Markov, it's always off, alright, so Markov first. And the moment it becomes a little bit tricky, then it doesn't get it right. But anyway, so that's sort of what we do. Good, so what I wanted to do next with you was, if you have questions, of course, you ask me. This bias reduction, so I just don't want to talk about it. There are a bit more theory here and there. But of course, the bias goes off when the sort of, when H becomes smaller, then bias disappears, you have consistency, and so on and so forth. One has normality. I don't want to talk about the linearity going. But I want to talk about multivariate distributions, right? So joint densities. Because my goal was, remember, we had M. And M was an integral of the bond times the joint density divided by the margin, D1. Marginal, we got. We know how to get it. Now we have to get the joint density, so we have the M coefficient. So the M, the regression, because that is more interesting for me. For you, I suppose, for more applied in the fall. Alright, let's see. And actually, the joint density is very easy. Alright, so it's sort of pretty much the same. That's an average. Okay? So 1 over n. So here, the kernel will be a two-dimensional kernel. Previously, we had a univariate Gaussian. Now we will have a bivariate Gaussian. Alright, so that will be a what? I have 3 variables. Then I will have a 3-variate Gaussian kernel. Or what? So sort of the kernel dimension grows, and then I plug in here, and then I go over. The rest is the same. Okay. Now, there is also something which you should pay attention to. That here, before here we had h. Now the dimension 2 becomes h squared. Okay. Now let me tell you why. Right? So what happens? If you had 3 variables, then it would be h to the power of 3. Right? Or 4, and so on and so forth. Right? Now, this is problematic. Right? But let's say we have some stretch of data points. These are data that we have here, univariate. And whenever we were choosing the bandwidth, then we had some h. And then we were checking, right, so here we have some data points. And then there are 2, right? That is what we have. And then in this basically area, then we have some neat observations that are very important for our calculation. Right? Now when we basically go to a 2-dimensional space, then things become a little bit different. What that this remains. So that will be, so this was x, now we have x and y. Alright? And the data will be distributed here. So there will be a lot of points here in the 2-dimensional space. So we have to estimate the joint PDF. Now, well here, we just had the stretch, and then we were looking how many data points are there. So here we also need the stretch, but the stretch will not be a line, or rather a square. Alright, so we will basically have, again, a very small square, and then we look, okay, how many points are here, and then we move, go around all of the space, and then we count how many there are, and calculate averages locally. So that's how 2-dimensional histograms work. With SNS, you can also generate 2-dimensional with the seaboard, 2-dimensional stuff. Right, so that's sort of what we have. Now, h is generally a small number. For example, for this exercise that we just did, Silverman gave us h to be 0.5. Right, so that's this length. So that's this stretch that we have here. But now let's say we have h.5 here to be also the bandwidth. So let's say here I have 0.5, and here I also have 0.5. What is the area here? What will be the area of this blue? It will be 0.5 to the power of 2.
Yeah.
The area here is 0.25, which is very small. So that's the place, the stretch that we have, such that we have to go look in there and then see how many data points we have. Remember that we need h to be very small. H should have gone to 0. Right? And then when h goes to 0, then the infinitesimal part or area where we go look how many points there are for a 2-dimensional goes to 0 faster than this. Because this goes to 0 at h, this goes to 0 at h squared. Alright? And that means that for a 2-dimensional, basically, density estimation, you need many more observations. Right? So much more. The number of observations we should be big. It's really big data, such that you have enough data points in each of these infinitesimal points. Right? Now assume that you have 3 dimensions. Then this will be a 3-dimensional. A cube. The cube will be like so. Alright? So that's a cube with dimension h. What is the volume? H squared, h cubed. So h times h. So here, even with, so if I have 3 dimensions, then this shrinks to 0, becomes a smaller, faster than that. And then it's faster than this. So for 3 dimensions, we even need more observations compared to the 2 dimensions. And now increasing. So let's say we go to the 4th, that will be h to the power of 4 the volume, the 4-dimensional space, and so on and so forth. So that means that with increasing dimensions, right, then you need more information, but we always sort of have restriction on the number of observations. It's always restricted, so we don't have infinitely many observations, you have 300, 3,000, 10,000 at most, right? So sort of a stable IID and normal information, right? So that would be actually a little problematic, right? This phenomena that I just told you, that the infinitesimal part shrinks to zero and becomes smaller, causes problems for us. And this is called how do you write dimension? Like this. This is called curse of dimensionality. So the dimensions become bigger, it becomes harder and harder to estimate a joint PDF. Well, oftentimes, so what does it mean? So if you come to think of it, so logically, so it means that, well, this would be very hard to do, well, by varied regression we just did, y on x, tap m risk premium on an asset on the market risk premium, right? So these two curves, sort of y on x. So if I basically start adding more variables, then I sort of fall in this problem. I will have the curse of dimensionality. Right? So, well, essentially, in the beginning, we stay with bivariate, non-variate, sort of bivariate regressions. And then I will give you some way of getting out of this curse of dimensionality, right? By introducing some new models, which are very simple and very easy to understand them. But that is what we have. So that was the general stuff. We can estimate this sort of two-dimensional stuff, and from that joint density, then you can estimate the marginal. But of course, once you have well, I mean, I did the what is it? I did the estimation of this in the very beginning. But of course, this is the same as doing bivariate, partially one out, y out, and you are left with the univariate. The integrations we can do easily. All right, so that we have the same stuff as we had before. Okay. Oh, in the programs we forgot to divide by age. Yeah, so. I stumbled on this, and why the curves somehow are different, but that will be the curve story. Now that I saw it, I remember in the slides. So the blue is the optimal one, orange is, H is smaller, so bias is smaller, but variance is bigger. No, H is smaller, so bias is smaller, variance is larger. Green is smoother, right? So I just came back to it, just to correct. So this I forgot to divide by H. Please fix it. Anyhow, so let's go back.
By H or by N?
No, by H. Look, I mean, that's also, well, here we have the summation of the weights divided by NH. I forgot H in my programs. That was a mistake. Anyhow, so let's continue with the bivariate one. See that I saw it here. So, the bivariate you can easily estimate, and then the joint can be estimated like that. So, well, I mean, the asymptotics and then estimating the calculating the expected value and so on and so forth, I will leave because the calculus is really involved. Right? So we have bivariate kernels, there will be a bivariate normal, and that is a little bit complicated. So I will leave it out. But what I want to go on is just to, well, this is just to tell you how to indeed get M. All right, so that's the M that we have started with in the very beginning of our session. I want to do some little calculation here. Alright, so we see how it works. And once we do, then we can go on and maybe do some application. Alright. Well, we said that m of x is the expected value of y given x evaluated at x. And that is integration over all of the values that we have of y, f of y given x, v y. Alright, so that is what we have. So now if I want to do an estimation of m, and y remains integration, the joint density up, and the univariate marginal in the denominator. So that will be m hat at the point x will be integration on r. So y is as is. But let's write it like at r, y, joint density divided by the margin. Or dy. Right? So that is what we have. Let's now plug it. So let's see the numerator. So I need an estimator for that one. We added 1 over nh squared. Okay. So it is not nh, but rather nh squared. Summation over all of the sample size that we have. And now comes the bivariate curve. So xi minus x. Alright, so that's sort of what we have. What y and x doesn't matter. Let's be in line with these lines. So yi minus y divided by h and xi minus x divided by h. Correct? Now this y is the pair that we have for the x. Let's bivariate. I have an x and I have a y. And this is also partial out. Right? So this is y. And then we do the integration with respect to that y. Divided by 1 over here nh, not h squared, it's one dimensional, summation pi, k of xi minus x divided by h. Right, that will be realistic. Now we have to maybe a little bit work on this to make it, well, sort of match what we had. And then we implemented in our previous basic stuff. And that is not hard. I mean, what we do is that, well, let's see what happens with the numerator. All right? So now, it is important for you to know that this is not a function of y. It's just 3 of y. So that's a scale. All right? So this is, which simply comes out of the integral. All right? So that is integration over r, 1 over nh squared, summation I, ki, yi minus y, h, xi minus x, h. Alright, so the integration I took simply in the numerator, because that's a scale, it's 3 of y, so I can take it out. Summation I, so 1 over nh, k of x minus xi divided by h, dy. So dy in the numerator. Alright, now let's see what we have. So what you can do is sort of play a little bit around with this. Alright, so to speak, you can do a change of variable in the sense that you set y to this variable as we have it there. Okay? Such that this whole thing, well, or sort of choose this to be v. Okay? Let's choose this as v. Okay? Now remember, we are doing integration with respect to y. Okay? So, and dy becomes, well, dy divided by h becomes minus dv. Okay? So, then dy becomes h minus h dv. So that's sort of what you have. And then the integration sort of sign is from minus infinity to plus infinity. But because we have a minus, then they swap. Alright? And then sort of, well, we can just work on the numerator only. Curse of dimensionality I told you. These are actually very important old concepts. Alright, so let's work on the numerator. So that would be integration rho of the R. Alright. So if I do this change of variable, then there is an H dV which shows up with one of those H's cancels. So we write here 1 over NH. Alright, in the numerator. Then, well, let's look at that. So this is the change of variable that we are doing. Alright. And that would mean that yi minus y divided by h is v. And that means that yi minus y is hv, or y is hv
YI
and
minus.
yi minus a. Thank you very much. A. This comes there, this goes there, so that is fine. So we can plug in for y. So that would be yi minus hv. Alright, so we have it somewhere there. And then there is a summation. Summation over I. K1, this is K1. That's the two-dimensional kernel. V xi minus x divided by h dy. D. So now this is our new variable. Right. So now we again can play around with the integral and the summation. Alright. So we swap the order of summation and integration as we have it here because these are all positive. Alright.
Okay, and so we have like n time h squared, but then at this time we only have n times h.
Yes.
Yeah.
That's true. Let's look at dy. It is minus h dv.
Yeah.
There is an h.
Mm.
So d1 becomes minus h dv, and then they cancel. There was two, right? And one of them actually goes off. Right. Now we swap the order of summation and integration. We can do that. Right. And once we do it, then, well, I mean, some terms actually remain. All right. But let's see. That is equal to 1 over NH. Well, that will be this integration of yi summation I K1V xi minus x divided by h d v. Yeah. So that's sort of y times that minus the other one, and this is 0. Wait, can you tell me why? Or when?
V.
Remember, well, let's say that this is a bivariate Gaussian.
Mm. V. So V cancel out.
That's so V, the kernel integration, so integration of V times the kernel will be 0 because the kernel is symmetric in each of its arguments. Right? So it's like the expected value. Like you told me in the very beginning, you remember? So there was a term that we had UKU integral and it was 0. That's the same.
So v k
That's right.
v v again.
Exactly. So that goes off. So That is why we basically don't have it, essentially. Well, I mean, that sort of goes off. So that's this term, but it disappears. Right? So that goes off. So only the first term remains. Okay? If you look at this, this is a kernel, bivariate kernel, and then you're integrating with V. Right? So it means you partial it out. So the marginal with respect to the second remains. Right? So that's like a density. And that is this. So remember, so here we have a yi times the weighting scheme. Right? And, well, and then we have this one also in the denominator. Okay? So now let's put everything together. So if we do that, then this minus h to the power of minus 1 cancels with this. Okay? And then what we are left with is that m hat at x is summation I w I divided by summation of the w. Right? So that is what we have. This and today, this sum function, estimation of this. Yeah? That's sort of very beautiful and very simple. You just need some time, a few hours. Since yesterday that we started, essentially I told you all of the history, stories that are behind all this. That was the kernel when Nadaraya was on this. Okay, so now I want to take you back to OLS. All right? If you don't mind. Well, actually, maybe I can write it. It's more. There are more over here. No, I'm not biased.
đi một vòng tròn xong thì quay lại cái hôm bữa hơn một bánh tráng luôn á, quá là đẹp. Dạ nào quá.
Okay, let's go back to OLS. Let's say we have some observations. Right? And I want that you again do the first order condition and stuff as you have there. So let's say we do the following. Can you minimize this in C? And do you know the solution? What is it? Why? By bar. The average.
Oh, yeah, there's a lot of line.
Maybe let me do that. Alright, shall we do the first order condition? So, with respect to C, that will be summation over I, well, minus 2 yi minus C equals 0. So if I simply take a derivative with respect to C. So minus 1, 2 comes down, the power becomes 1. Okay? Now it's reduce cancels because that's a scale. And here we have summation of yi equals minus becomes plus summation of C. Right? You agree? So that this is indeed, well, the sample let's say is n. So that is n times C. Good. So then C becomes 1 over n summation yi, which is y bar, as we told us. Alright, so that's sort of if you do that, means like regressive y only constant and residual. Then the estimator will be simply by y. So that is something good. You remember that. Now I will do a different. Can I buy it? So there is a base, some W that I put here. Can you do the minimization now? This is beta least squares. So this will be summation W Y I. Right? So what do you see? That's the same. So that is a beta least squares, which you have known or supposed to know. Right? So that was a beta least square. Right? So this problem can be written like a beta least squares. So the estimation is very easy because you have this square, that sort of it's OLS, beta OLS. So you can indeed pass it to whatever software and then do the estimation really very fast. Well, okay. If it is beta least squares, maybe let me change this C to M. All right. All right. All right. So that's the function. So the base you calculate for whatever values, you sort of pass into the OLS, and then you get the or sort of estimate as simple as that. All right. But actually, if it is like this, if it is so simple, then one can do more with it. Some other stuff. So I'm excited when I come to this part of nonlinear. For example, let's say we have data that look like so. Okay, these are the data. And however we estimate, and we will say, okay, let's take an H and take an average. Right, so that was what we were doing, beta. So this was the H, and then in here, we were focusing on those points in the very beginning when we were getting an average here. Right? But why do we actually do an average? Why not? So average will be a simple log, right? So we will go. So why not actually do a little line? Something like this. Why not? So instead of having locally constant, which is what we have been doing so far, we can do something which we call it locally linear. Right. So you estimate n, and you estimate b. Right. So that will be the slope that you have in here. Okay. And this will be the slope of n. Alright. So you can basically maybe look at it like so. So you can basically look at it like xi minus x. Right? To the power of t. is xi minus x. So I'm centering it at this x.
Mm.
Such that n at xi, right, so sort of, remember, the estimate will be different. That is a weighted piece square. You can do the calculations again. Where is my? Alright. So that will be a little bit different. So here we will be minimizing this in n and beta. Alright? So this is indeed called local linear. Which we can use it to sort of estimate the derivative of n at a certain point. That will be. Right? Well, so to speak, this m of x, we can write a Taylor expansion of it. Alright? At x, or well, at some point, which will be m itself, plus a small, well, you remember Taylor expansion, the first term is linear, right? And that's the linear term. Right? And this linear term will be 0, right? Exactly at the point that you are calculating the Taylor expansion. Remember, so say g of x if it is g of say z, right? So if you write the Taylor expansion at x, it will be g of x plus g prime at x times z minus x plus the other terms. So that's the same. That's xi minus x. But as m, that's the main term at the x. And then this is the other term. So I basically subtract this x from xi such that this is actually 0 in this sense. The g at x, alright, it is g of x on the right hand side, plus all of the other terms, which are 0, because they are z minus x. So if I plug for z equal to x, and all of these terms go off. Right? But this quantity that we have as the slope, which is beta, indeed is the derivative of the m locally. Alright? So indeed this is helping us to understand how does m change when x changes. So that's the derivative essentially. So because the derivative of m with respect to x, indeed is the derivative of the expected value of y given x with respect to x. That's the marginal effect. It's the marginal effect of x on y, on going over. You started at 1. Let's have the break. I think Min was his input, right? He left without telling him that we have a break. Let's have this break. Now we can see with this local linear and so on and so forth. So we'll explain them a bit further so that you know. But they are so simple. They are.
So simple.